China is preparing to spend billions of dollars on artificial intelligence hardware that does not come from Nvidia. That should not be possible. The country cannot freely purchase Nvidia's most capable processors. It cannot import the EUV lithography machines used to manufacture the world's leading chips. And its domestic accelerators still fall behind the best American hardware in several important measurements. Yet Huawei's processors are entering Chinese data centers at growing scale. This matters far beyond a competition between two technology companies. The chips installed today determine which software developers use, which cloud platforms expand, which technical standards become dominant, and which government retains leverage over the artificial intelligence those systems will eventually power. American export controls were designed to slow China's access to advanced computing. They imposed real damage. Supplies disappeared, production costs increased, and some Chinese companies were forced to redesign entire products. But the restrictions also created an unintended incentive. China no longer had to build processors that were immediately faster than Nvidia's. It needed processors that could be manufactured, delivered, repaired, and expanded without waiting for approval from Washington. That changed the contest completely. Huawei's strategy now rests on four connected advantages: manufacturing advanced silicon with older equipment, accepting costs that ordinary companies would reject, linking huge numbers of processors into unified systems, and creating enough domestic demand to support the entire operation. None of this proves that China has overtaken Nvidia. It has not. The more unsettling possibility is that China may no longer need to overtake Nvidia to escape its dependence on the company. To understand how that became possible, we need to return to the company that found itself at the center of the blockade. Ren Zhengfei founded Huawei in Shenzhen in 1987 with modest capital and a narrow business selling telecommunications equipment. Instead of beginning with the most profitable urban markets, Huawei developed equipment for rural and underserved regions where larger foreign suppliers had less interest. That work was not glamorous, but it gave Huawei experience solving difficult infrastructure problems under tight cost constraints. The company gradually expanded from telephone switches into mobile networks, enterprise systems, smartphones, and advanced telecommunications equipment. By the late 2010s, Huawei had become one of the largest technology companies in the world. Its equipment operated across numerous countries, while its smartphones competed near the top of the global market. That rapid expansion also placed Huawei directly inside a much larger confrontation. In May 2019, the United States added Huawei to its entity list, restricting the company's ability to purchase American technology without government authorization. Washington argued that Huawei posed national security risks. Huawei rejected those allegations, but the commercial consequences were immediate. Losing direct access to American suppliers was only the first layer. Modern semiconductor production is international. A processor may be designed in China, manufactured in Taiwan, patterned using Dutch lithography systems, tested with American equipment, and built with software containing American intellectual property. That gave Washington influence over suppliers located far beyond the United States. When the restrictions were expanded, companies using certain American technology could no longer manufacture advanced Huawei-designed chips without authorization. TSMC, the Taiwanese foundry that had produced Huawei's most sophisticated processors, stopped accepting new Huawei orders. The damage reached far beyond a missing shipment. Huawei had developed strong chip designs through its HiSilicon division, but HiSilicon did not own the advanced factories required to manufacture them. When access to TSMC disappeared, Huawei could still create processor blueprints, yet it could no longer reliably turn its newest designs into physical products. The restrictions also affected electronic components, design software, manufacturing tools, smartphone services, and relationships with international suppliers. Parts that had taken years to qualify could suddenly become unavailable. Huawei's consumer business suffered heavily. Its smartphone position declined, and the company was forced to sell its Honor phone brand. Many analysts believed the restrictions had created a technological barrier Huawei could not cross. The company's response was not one miraculous invention. It was a long and expensive substitution campaign. Huawei began examining its products component by component. According to Ren Zhengfei, the company eventually replaced more than 13,000 parts affected by restrictions and redesigned thousands of circuit boards. That number comes from Huawei itself, and replacement did not necessarily mean that every part was immediately equal to its foreign predecessor. Some substitutes would have been more expensive, less efficient, or harder to obtain. Others required surrounding hardware and software to be redesigned before they could function properly. But each substitution removed one potential point of foreign control. Huawei also accelerated Harmony OS after losing access to important parts of Google's mobile ecosystem. It developed alternatives to foreign enterprise software and strengthened relationships with Chinese suppliers that previously lacked enough customers to justify large investments. This produced a powerful industrial feedback loop. Huawei needed domestic components to survive. Chinese suppliers needed a large customer willing to test imperfect early products. Government support reduced part of the financial risk, while Huawei provided engineering experience, purchase volumes, and a path into commercial systems. A supplier did not have to match the global leader on its first attempt. It only had to produce something Huawei could improve, integrate, and purchase again. The sanctions therefore changed the economics of Chinese semiconductor development. Before the restrictions, buying a proven foreign component was often faster and cheaper than building a domestic alternative. After the restrictions, the foreign component might disappear with the next policy decision. Reliability was no longer only an engineering measurement. It became a geopolitical one. At the center of Huawei's response was a division that had been established long before the crisis. HiSilicon was created in 2004 to design semiconductors for Huawei's telecommunications and consumer products. It is a fabless chip designer, meaning its engineers can develop processor architectures without owning the fabrication plants that physically construct them. This division gave Huawei something sanctions could not instantly erase: years of accumulated chip design knowledge. Among HiSilicon's most strategically important projects was the Ascend family of AI processors. These accelerators are built to perform the enormous volumes of mathematical operations required for artificial intelligence training and inference. The Ascend 910C became especially important. It was not a direct replacement for Nvidia's most advanced hardware, and manufacturing constraints initially limited its availability. But it offered Chinese data center operators something strategically valuable: an AI processor designed under Chinese control and supported by a domestic company that was not preparing to abandon the market. Reported production plans later suggested Huawei wanted approximately 600,000 Ascend 910C units in 2026, with as many as 1.6 million dies distributed across parts of the wider Ascend portfolio. Those figures are targets rather than guaranteed deliveries. A fabricated die is not automatically a finished accelerator, and production still depends on memory, packaging, testing, power systems, networking, and acceptable yields. Nevertheless, targets at that scale reveal that Ascend is no longer being treated as an experimental backup. Huawei is attempting to turn it into the computing foundation of China's AI industry. But designing that escape route was the easier half of the problem. The processor still had to be manufactured with microscopic precision. China was blocked from acquiring the EUV machines normally associated with the world's most advanced production lines. Without them, many observers assumed Huawei's designs would remain trapped inside engineering software. To turn those designs into working silicon, SMIC would have to force an older generation of machinery to perform a task the semiconductor industry considered technically possible, but commercially irrational. The older technology was called deep ultraviolet lithography, or DUV. Lithography works by projecting patterns onto light-sensitive material covering a silicon wafer. Those patterns help define the microscopic transistors and connections that eventually become a processor. As chip structures shrink, placing those patterns accurately becomes much harder. The world's leading factories use extreme ultraviolet lithography for many of their most demanding layers. EUV operates at a much shorter wavelength than DUV, allowing manufacturers to print extremely fine structures with fewer patterning stages. Only one company, the Netherlands-based ASML, supplies production-scale EUV systems. These machines contain extraordinarily complex optics, light sources, vacuum chambers, and positioning systems. China has been prevented from purchasing them. That restriction created a formidable barrier, but not an absolute physical limit. SMIC, China's largest contract chip manufacturer, still had access to older DUV equipment. Rather than producing a difficult layer in one exposure, engineers could divide its pattern across several separate operations. This technique is broadly known as multiple patterning. Imagine that one stencil cannot reproduce every line in a complicated drawing without the lines blending together. The solution is to separate the drawing into several simpler patterns. One stencil creates the first set of lines, another adds the next set. Additional deposition and etching steps refine the structure until the combined result approaches the required density. On silicon, however, every pass must align with structures that may be only nanometers apart. A tiny overlay error can damage electrical connections or make the entire die unusable. More stages also mean more opportunities for contamination, variation, and defects. The wafer spends longer moving through the fabrication line. More masks are required. More equipment time is consumed. Production capacity falls while the cost of each usable processor rises. This is why saying that DUV can produce an advanced chip does not mean it can produce that chip as efficiently as an EUV-equipped factory. The difference becomes visible through yield, the percentage of usable dies obtained from a processed wafer. A wafer contains many copies of the same processor design. If defects ruin a large proportion of them, the cost of every surviving die increases. The factory has paid to process the entire wafer regardless of how many chips ultimately work. Early reporting indicated that yields for some Huawei and SMIC advanced processors were extremely low. Estimates varied because neither company publicly disclosed complete production data. More recent reporting suggested the yield for Huawei's Ascend 910C improved from roughly 20% to nearly 40%, with further improvement targeted. That is meaningful progress, but it remains far below the efficiency expected from a mature production line at a leading foundry. It also should not be confused with the yield of every advanced chip SMIC manufactures. Different designs, process generations, die sizes, and packaging methods produce different results. In a normal commercial market, such disadvantages might make the product uncompetitive. A customer could simply purchase a faster processor made more efficiently by TSMC. China is not operating under normal market conditions. A domestically available chip carries strategic value that does not appear in its benchmark score. If the alternative is a foreign accelerator that may be restricted, delayed, or denied, paying more for a less efficient domestic product begins to look like insurance. State support changes the calculation further. China has directed enormous resources toward semiconductor development through national funds, regional investments, tax incentives, industrial parks, research programs, and procurement policies. This does not eliminate the engineering problems. Money cannot instantly create decades of manufacturing knowledge, but it allows companies to survive low yields, purchase more equipment, run additional experiments, train specialists, and improve a process that might otherwise be abandoned after its first commercially unsuccessful generation. Huawei also supplies something equally important: continuous demand. Reported plans called for production of around 600,000 Ascend 910C processors in 2026, roughly twice the previous year's intended level, and as many as 1.6 million dies across relevant Ascend products. Those numbers require caution. They reportedly include inventories and internal assumptions about future yields. A die must still be packaged with memory and other components before becoming a usable accelerator. Production targets can also be missed. High-bandwidth memory remains a serious constraint. Advanced packaging, interconnect hardware, power delivery, cooling systems, testing capacity, and manufacturing equipment can each limit the number of complete systems Huawei delivers. Even so, volume creates its own advantage. Every production run provides new defect data. Every installed system reveals software failures. Every large customer gives engineers another workload to optimize. What begins as an inefficient workaround can gradually become an industrial process. Huawei's next move shows that it understands the race cannot be won through fabrication alone. In September 2025, the company publicly presented a multi-year Ascend roadmap. It included the Ascend 950PR, scheduled for the first quarter of 2026, and the 950DT, planned for later in the year. The two designs target different demands within modern AI systems. Generative AI does not perform one uniform task when answering a request. During the pre-fill stage, the system processes the user's input and builds the context needed to generate a response. During the decode stage, it produces the response token by token. Training creates another demanding workload involving huge amounts of computation, memory movement, and communication between processors. Huawei positioned the 950PR toward prefill requirements, while the 950DT was designed with decode and training-related workloads in mind. This specialization allows the company to optimize different parts of the AI pipeline rather than expecting one processor to perform every task equally well. But the more important shift is occurring above the individual chip. Nvidia's best accelerators retain major advantages in performance, energy efficiency, manufacturing technology, memory systems, and software maturity. Huawei's response is to connect increasing numbers of Ascend processors into enormous computing systems. Its Atlas SuperPOD architecture is designed to make thousands of physical processors function as one coordinated machine. Huawei has described configurations scaling to 8,192 processing units. This is an immense engineering challenge. AI training repeatedly transfers data between processors. If communication is slow, the accelerators spend valuable time waiting instead of calculating. Adding more chips can increase theoretical computing power while delivering disappointing real performance. The interconnect therefore becomes almost as important as the processors themselves. Huawei's long experience in telecommunications gives it relevant knowledge in networking, optical connections, system control, and large-scale infrastructure. Instead of asking whether one Ascend processor can defeat one Nvidia accelerator, Huawei wants customers to compare complete clusters. That does not automatically erase the performance gap. More processors consume more electricity, require more cooling, occupy more space, and create additional failure points. But if China can manufacture and deploy enough of them, aggregate computing capacity can compensate for part of the weakness of each device. This helps explain why major Chinese technology companies are testing or adopting domestic hardware. ByteDance was reportedly preparing to spend more than 40 billion yuan, approximately $5.6 billion, on Huawei Ascend processors in 2026. Because neither company publicly confirmed every detail of the reported arrangement, it should be understood as a procurement plan rather than a completed transaction. Alibaba, Tencent, Baidu, cloud providers, and state-linked projects have also been connected to increasing domestic chip adoption. Their decisions are influenced by more than performance. Availability, regulatory policy, future supply security, software support, and access to technical assistance all matter. A slightly faster processor has limited value if the customer cannot obtain enough units to build its data center. That places Nvidia in an extraordinary position. The company developed the H20 specifically to comply with American export rules for China. Even then, tighter licensing requirements prevented billions of dollars in expected sales and contributed to a multi-billion-dollar charge. Limited licensed shipments later resumed, but access remained small and uncertain compared with the market opportunity Nvidia once expected. Meanwhile, Chinese regulators and procurement policies increasingly encourage domestic alternatives. Nvidia was being restricted by Washington while its Chinese customers were being pushed toward Huawei by Beijing. Yet producing processors and winning protected domestic orders still do not create a complete AI ecosystem. Nvidia controls something far more difficult to reproduce than a chip: the software habits, tools, libraries, and accumulated knowledge of millions of developers. Whether China can escape that dependency will determine if Huawei has built temporary resilience or the foundation of a genuinely separate technological world. That software advantage is called CUDA. Over nearly 2 decades, Nvidia built far more than a programming platform. It created libraries, development tools, documentation,